Okay, in this video we are going to talk about equilibrium constant and exothermic and endothermic reactions. We'll talk about this in a second, in a couple minutes. We talked about, or at least I reviewed, exothermic and endothermic reactions in a background video in the previous week, but we might as well review it again. If you have some reaction, here's pretend reaction, A turns into B, and I'm going to plot how much energy A and B have. And let's say that A has a lot of energy, B has not so much energy. So if you're up high on the y-axis, you have a lot. If you're down low, you have less. In this pretend reaction, A has more energy than B. But if high energy A turns into low energy B, where did the extra energy that A had, where did it go? That's certainly not in B, because B has less energy. So a more accurate description of this reaction is that you would write A turns into B, plus it releases some energy, or you can, sometimes that energy will be represented as heat. So if you see a chemical reaction where it says something turns into something else, plus it produces energy or heat, that means that heat or energy is released by A to the outside world. And this kind of reaction is called an exothermic reaction. Exo means outside, thermic means heat. So heat or energy gets released from A to the outside world. That's what exothermic means. Endothermic is the opposite, so let's pick some different pretend chemical reaction. X turns into Z, and if you plot the energy of X, maybe it's somewhere down low, and Z is up higher. And the only way that X can turn into Z, so low energy X turns into higher energy Z, is if you have to feed some heat or energy into molecule X in order to turn it into Z. And if you have heat or energy on the left side of the arrow, where you're feeding it into this molecule, this is called an endothermic reaction. And endo means going inside of, thermic means heat again, so heat or energy goes inside of this X molecule and turns it into some higher energy molecule, Z. So we're going to talk about that in this video, but that's enough background information that you're going to need when we talk about endothermic and exothermic. Now, as far as this slide is concerned, just in case it was not clear, every exercise that we've done in these videos has told you what the temperature was. And there's a reason for this. The reason is that the equilibrium constant for a reaction depends on the temperature. In other words, if you make a reaction take place at a higher temperature, the equilibrium constant will probably change. If you make it take place at a lower temperature, equilibrium constant will probably change. And this is actually going to relate back to endothermic and exothermic. And here is an example of what I am talking about. This is kind of a crazy chemical reaction. It's kind of interesting, and we used to do it in the actual lab back when we would meet in person. But this stuff on the left side, this complicated looking stuff here, it is colored pink. It has a pink color when it's dissolved in water. And there it is, right? That's a picture of it. This stuff on the other side of the equation, it has a completely different color. It's colored blue, and there it is. There's a picture of it dissolved in water as well. And so you have this pink stuff that can turn into this blue stuff, and vice versa, because the reaction can run forward and backwards. What's weird about this is that if you take a test tube with this reaction taking place in it, and you keep it at a cold temperature, you keep it at 5 degrees Celsius, the liquid in the test tube will look pink, because most of the stuff in the test tube is this stuff over here. If you warm up this chemical reaction, and you make the temperature of the test tube get up to 75 degrees Celsius, the liquid in the test tube turns a color of blue, which means this stuff, there's not so much of it anymore. The pink stuff, not so much. And the reaction gets shifted over to the right side, to the blue side. So now what does this have to do with Le Chatelier's principle and endothermic and exothermic? What this means, if we make the temperature go up, right, we're making the temperature go from 5 to 75. If we make the temperature go up and the reaction gets pushed this way, what that means is heat must be on the left side of the equation. Same basic thing that we were talking about with Le Chatelier's principle. We are at equilibrium. Let's say we're at equilibrium over here, and we have mostly pink stuff. But if we make the heat go up, heat goes up there, because heat is on the left side of the equation, the reaction is going to get pushed to the right side to get back to equilibrium, and it's going to get pushed to the blue side. And this is only true if heat or energy is on the left side of the equation. What that means is we know, just by doing this little experiment, that this reaction right here is endothermic. This only happens if you heat up a chemical reaction and you push the reaction to the right side. It has to be endothermic. If it was the other way, if heat was on the right side of the arrow and we warmed up the test tube would have got pushed over to the contents of the test tube would have got pushed over to the pink side, but it didn't. It got pushed over to the blue side. So this cannot be the case. There must be heat or energy on the left side of the arrow in this case, which means we figured out, just by doing this little experiment, that this reaction right here is endothermic. You can think of this type of experiment as being basically a special case of Le Chatelier's principle. The reaction is at equilibrium. There's a certain amount of heat or energy. But if we mess with the equilibrium by boosting up the temperature, we're going to disturb the equilibrium. And to try to get back to equilibrium, the reaction is going to get pushed to the right side. And that's only true if you have an endothermic reaction. Here's a summary of what I've been trying to say. If the temperature of your reaction goes up and the equilibrium constant also goes up, in other words, if I have A turns into B, and remember the equilibrium constant for this pretend reaction is the concentration of B at equilibrium divided by the concentration of A at equilibrium. If the temperature goes up and the equilibrium constant goes up, that means this side went up and this side went down. And if this side goes up and this side goes down, that means the reaction got pushed forward. And that means heat or energy must have been on the left side of the equation, and that means the reaction must be endothermic. And that means heat or energy must be on the left side of the arrow, and that means the reaction must be endothermic. If the temperature and the equilibrium constant go in opposite directions, in other words, if the temperature goes up and the equilibrium constant goes down, that means if the equilibrium constant goes down, that means the left side got bigger and the right side got smaller, which means the reaction got pushed backwards. And if the reaction got pushed backwards when the temperature goes up, that means heat or energy is on the right side of the arrow, and that means you have an exothermic reaction. And these last two rows, they say the same thing as the first two rows, but they talk about when the temperature goes down. The punchline here is that if the temperature and the equilibrium go in the same direction when you move them, then the reaction is endothermic. If the temperature and the equilibrium constant go in opposite directions when you move them, then the reaction is exothermic. And that's the end of this video. See you in the next one.
Well, I was rolling down the road in some cold blue steel. I had a blues man on the back and a beautician out the wheel. We're going downtown